Your next reading is hypothesis testing, and let us go by Elvis. First, Elvis says define a hypothesis, describe the steps of hypothesis testing, and describe and interpret the choice of the null and alternative hypothesis. First, let's define hypothesis. The literal meaning of hypothesis is some assumption, some premise. Let's see how it has been defined here. A hypothesis is an assumptive statement about a particular problem that is under consideration, about an idea, or maybe some characteristic of the population. Let's say this is the population of 500 stocks. I just want to assume something about this population, and then I want to test whether my assumption is correct or not. So it could be just my assumption about this population, my opinion. So it could be a claim, a belief about a given issue. So therefore, we will conduct some statistical test to establish whether the claim, the opinion, or the belief is correct or not correct. So what we do in hypothesis testing, we just draw some samples from this population, collection and examination of this population through some representative sample, and using this sample we will determine if the hypothesis, our assumption, our opinion or claim is either true or false. So that is the little description of hypothesis. Now next we have to describe the steps of hypothesis testing. So they're coming right here. The first step is that we will first state what is the hypothesis. So these are the several steps we will take. The first step is to state the hypothesis, state our claim, our assumption, whatever that we want to test. The second step, select the appropriate test statistic, means some specific aspect of the sample that has been taken from the population. That's the second step. Then specify the level of significance. We'll discuss this. 1%, 5%, 10%. After we have specified the level of significance, we will state the decision rule. All these steps will be discussed as we go along. State the decision rule regarding the hypothesis. Then the next step is calculate the sample statistic, the sample mean or something that we are interested in. And finally, based upon the sample statistic, we will make a decision regarding the hypothesis, whether it was correct or incorrect. Next, null versus alternative hypothesis. Okay, what is null hypothesis? Null hypothesis is denoted by H0. This H0 basically represents the current state of knowledge about the population parameter. Now this is your population, and let's say this is the population mean. So our null hypothesis H0 could either be that mu is equal to mu naught, or mu is less than equal to mu naught, or mu is greater than equal to mu naught. The alternative hypothesis, denoted by H1, takes an opposing position. So basically H1 is something that if calculated and if concluded to be true, then it means we will reject this null hypothesis. So basically H1, the alternative hypothesis, if concluded, it would mean that there is sufficient evidence to reject the null hypothesis. All right, next there are different types of tests. One-tailed test, two-tailed test. Let us discuss that. One-tailed test, given here, directs all of the significance level alpha, we'll discuss that alpha later on, to the testing of statistical significance in just one direction. Here or here. This is called one-tailed test, left side or the right side. So the aim is to test the possibility of change in one direction, left or right, and completely disregard this region. Disregard the possibility of change in the other direction. But a two-tailed test represented somewhere this form, it considers the possibility of change in either direction, left or right. It looks for a statistical relationship in both the positive and the negative direction of the distribution. So we have distinguished between one-tailed and two-tailed test of the hypothesis in the previous learning outcome statement. Let us jump to the next one. So the next LOS says explain a test statistic, type 1 and type 2 errors, level of significance, and how significance levels are used in hypothesis testing. So first of all, a test statistic is a quantity calculated based on a sample. And let's say this is your population and you have drawn a sample out of it. So a test statistic is a quantity calculated based upon the sample, and this value is the basis for deciding whether or not to reject the null hypothesis. How do we calculate test statistic? This is the formula. Test statistic is equal to sample statistic, the hypothesized value that we want to test, our original hypothesis, and the standard error of sample statistic. This is what we have already discussed in our previous reading. Okay, now using this test statistic, we can subdivide the set of values that can be taken by this test statistics into two regions. The non-rejection region, which is consistent with H0, and the rejection region, this one, also called the critical region, which is inconsistent with H0. So this region is inconsistent with H0. This is called the critical region, and this is the non-rejection region. Right? So if the test statistic has a value found within the critical region, these, we reject H0. We reject the null hypothesis. All right, so this is what the test statistics is all about. Next we have the type 1 and type 2 error. Let us discuss. The type 1 error occurs when we reject a true null hypothesis. The null hypothesis was true, but we made a mistake. We rejected the true null hypothesis. And to the contrary, type 2 error, it is the failure to reject a false null hypothesis. Null hypothesis was false, but we did not reject it. So type 1 error occurs when we reject a true null hypothesis, and type 2 error occurs when we fail to reject a false null hypothesis. All right, so then it further says significance level. Basically, significance level is the probability of making a type 1 error. Level of significance, it is denoted by alpha. It represents the probability of making a type 1 error. And what is type 1 error? The type 1 error occurs when we reject a true null hypothesis. So the probability of making a type 1 error is basically the significance level represented by alpha. So how do we use this significance level in our hypothesis testing? Remember, we use alpha to determine the critical values that subdivide your region into acceptance and rejection regions. So this alpha is what helps us determine the critical values that divide your distribution into the area of acceptance versus area of non-rejection. Sorry, area of rejection and the non-rejection regions. Alright, next is explain a decision rule, the power of a test and the relation between confidence interval and hypothesis test. So basically what is a decision rule? The decision rule is basically a procedure followed in hypothesis testing when deciding whether to reject the null hypothesis or not to reject the null hypothesis. We'll explain this as we go along. So let us apply this concept in different types of tests. Left one-tailed test. We are talking about this. So the decision criteria here is that our alternative hypothesis is that parameter, if this is x, the parameter is less than x. So decision rule here is reject H0, the null hypothesis, if test statistics is less than the critical value and it falls here in this rejection region. Otherwise, do not reject the null hypothesis. Then the right one-tailed test, this one. Here, this is your alternative hypothesis. The decision rule here is reject the null hypothesis if the test statistics is greater than the critical value, if the result falls in this critical region, then reject the null hypothesis. Otherwise, do not reject the null hypothesis. And lastly, in the two-tailed test, we will do this all. It's just an overview. We will apply these concepts in actual questions. So just get an overview and then we will apply it there. All right. So in the two-tailed test, this is the critical region. So here is the alternative hypothesis that the parameter is not equal to x. So the decision rule here is reject the null hypothesis if the test statistics is greater than the upper tail here and less than the lower tail critical value. So if the result falls within this region, then reject the null hypothesis. Otherwise, do not reject the null hypothesis. Okay, the next area here is the power of a test. What is it? The power of a test gives the probability of correctly discrediting and rejecting the null hypothesis when it is false. So when null hypothesis is false and you successfully reject it, you discredit it. So this is what you call the power of a test. So it is calculated this way. The power of a test is equal to 1 minus probability of making a type 2 error. Simple as that. Now whatever we have done, now let's try to apply these into the actual questions and then we will make more sense out of it. Alright, so here's a good question. So whatever we have done so far, now let us try to apply in this question, so it will refine whatever we have just done. A researcher has gathered data on daily returns on a portfolio of call options over a recent 250-day period. The mean daily return has been 0.1% and the sample standard deviation of daily portfolio returns is 0.25%. The researcher believes that the mean daily portfolio return is not equal to 0. Okay. Now first, construct a 95% confidence interval for the population mean daily return over the 250-day sample period, and then later construct a hypothesis test for the researcher's belief. Now let us do first part first. Since we have been given a sample size of 250 days, standard deviation 0.25. First we need to calculate the standard error. How do we do that? The standard error of the mean is sample mean is equal to standard deviation square root of the size of the sample. So it's going to be 0.25 upon square root of 250. So it's going to give you 0.0158%. Okay, we are just doing the first part of the question. Now the question says that construct a 95% confidence interval. Okay, so it means if 95% is the confidence interval, that means the level of significance is 100 minus 95, that is 5%. So the 5% level of significance, the critical z values for the confidence interval can be calculated this way. Since it's a two-tailed test, as you can see, it says not equal to. If you just can see here, the mean daily portfolio is not equal to 0. So it's a two-tailed test, which means this 5 must be divided with 2. So that's 2.5. So we are talking about the test statistic of 0.025. The two-tailed test, it's 1.96 standard deviation from the mean, right? Okay, and then the other side would be negative z 0.025, negative 1.96. All right, so we have our numbers. Let us find out the confidence interval. So confidence interval, as we have discussed in our previous reading, is equal to point estimate plus minus, we already have them, the reliability factor multiplied by the standard error. Simple. Plug in the numbers and you will get the result of your part 1 to this question. All right, so here we go. This is the point estimate, 0.1 plus minus reliability factor, that is 1.96 standard deviations from the mean, and standard error we calculated in our previous part to the question, 0.0158. So its simplification would give you this confidence interval. If you simplify this with a plus sign, you will have 0.131%, and when it 0.1 minus the numbers, you get 0.069%. So this is what you call your confidence interval at 95%. All right, now let's do the second part. Construct a hypothesis test of the researcher's belief. Okay, first of all, we need to specify the null and alternative hypothesis. That's the first step. So the null hypothesis here is the one the researcher expects to reject. So the null hypothesis is that mean is equal to 0, and the researcher believes that it is not equal to 0. So the alternative hypothesis is that mean is not equal to 0. Since the null hypothesis is an equality, this is a two-tailed test at 5% level of significance. All right, so it can be shown this way. Now, this is the critical region. This is the critical region. So if your test statistics is less than negative 1.96, or if it is greater than 1.96 in this region, then we will reject the null hypothesis. Now let us use the standard error of the sample mean. Let us calculate the test statistic. So we have the mean daily return, that is 0.1%. If you remove the percentage sign, it's going to be 0.01 divided by the standard deviation, removing the percentage sign, 0.025 divided by the square root of the sample size. So when you simplify this, the result comes out to be 6.33. So as you can see, our result, our test statistics, it is greater than 6.33, that is greater than 1.96. It falls in this region. And we already agreed that if our test statistics is greater than 1.96 or less than negative 1.96, we will reject the null hypothesis. So we can now reject the null hypothesis that the mean daily option return is equal to 0. It is not. Alright, next question. To test whether the mean of a population is greater than 20, the appropriate null hypothesis is that the population mean is, if this is what we want to verify, then your null hypothesis has to oppose this. So it means your null hypothesis has to mean is less than equal to 20. And this is the alternative hypothesis, that the population mean is greater than 20. So that makes C to be the correct option. Next, which of the following statement about hypothesis testing is most accurate? A type 2 error is rejecting the null when it is actually true. Wrong. That is type 1. That's a type 1, rejecting the null when it is actually true. The significance level equals 1 minus the probability of type 1 error. Wrong. The significance level equals probability of type 1 error. So it is incorrect as well. A two-tailed test with the significance level of 5% has Z critical values of plus 1.96 from the mean and negative 1.96. That is true. We've just done it a little while ago. So that makes C to be your correct option. Next, for a hypothesis test with probability of type 2 error of 60% and a probability of type 1 error of 5%, which of the following statement is most accurate? The power of test is 40%. Power of test is 1 minus probability of type 2 error. 1 minus 60% is 40%. So this part is correct. But look at the remaining part of the option. And there is 5% probability that the test statistic will exceed the critical values. This is not always true. This is not always true, since the null may be false and the probability of rejection is unknown. So we can't say that. B, there is a 95% probability that test statistics will be between the critical values if this is a two-tailed test. Again, it is not necessarily true. The reason being that the null may be false and the probability of rejection is unknown. Look at option C. There is 5% probability that the null hypothesis will be rejected when actually true, and that is exactly the type 1 error. We discussed a type 1 error a little while ago. Type 1 error occurs when we reject a true null hypothesis, and it is 5%. So this one is true. And then the probability of rejecting the null when it is false is 40%. So probability of rejecting a false null is given by 1 minus the type 2 error, which is given here as 60%. So it's going to be 40%. So yes, it perfectly makes sense. C is the correct option. Next, if the significance level of a test is 5% and the probability of type 2 error is 15%, what is the power of the test? We've just done it a little while ago. The power of the test is 1 minus probability of type 2 error. So it's going to be 1 minus 0.15. That is 85% or 0.85. So that makes A to be the correct option. Okay, the next LOS says distinguish between a statistical result and an economically meaningful result. Now this is an interesting LOS from very practical point of view. Well, we may use statistics for making decisions, but we cannot just ignore the economic reality of our decisions. When we are dealing with investment, some of the factors that may affect the economic feasibility may be beyond the domain of statistics, like regulations, like taxes, like political risks, and many other costs. So let us assume we want to invest in a country X, for example, and we use our statistical modeling to determine what's the EPS going to be. and our statistical modeling tells us that EPS is going to be a significant amount. Now this is just the stats part. What we have totally ignored is that maybe the level of taxes in that country would be very high. There might be some risk of expropriation, the risk of not being able to repatriate profit back to the home country. Right? So there are many risks involved. Exchange rate risks, changes in the tax legislation, political risk, risk of expropriations. So that's why we just cannot ignore the economic consequences. So just focusing on statistical return would not be sufficient. So making decision based on just statistical analysis is not enough. It's not a guarantee of return. Then we can say that the economic influences to be considered in decision making, and then statistical computations will just complement our efforts, our analysis, but we cannot rely solely on statistical results. So this is the specific purpose of this learning outcome statement. Your next LOS is explain and interpret the p-value as it relates to hypothesis testing. What basically is p-value? P-value is the lowest level of significance at which we can reject the null hypothesis. Now, how does it look like? Let's say this is your normal distribution. So this region here, the area, let's say this is denoted by Z alpha. So the area to the left of Z alpha is the p-value, or this is the left tail test, or it's the right tail test, and let's say this is Z alpha. So in this case, the area right of Z alpha is the p-value, and if it's a two-tail test, then the p alpha, or what would you call the alpha, the p-value, it is the sum of the area of the tails is the p-value, this one and this one. So basically the strength of the evidence against null hypothesis increases as the p-value becomes smaller. For left one tail test, the p-value is given by the probability that lies below the calculated test statistics. For the right tail test, the p-value is given by the probability that lies above the calculated test statistic. And for two-tail test, I just told you a little while ago, the p-value is basically the sum of probabilities in the two tails. So let us do a question to enhance our understanding. A survey carried out using a sample of 50 CFA charter holders reveals an average IQ of 105. Previous studies have shown that IQs are normally distributed with a standard deviation of approximately 20 using a 5% level of significance. Is the mean IQ of CFA charter holder greater than 100? Now first let us set up the null hypothesis. The mean is equal to 100. The alternative hypothesis, which you can denote by HA or H1, is that mean is greater than 100. So what you're looking for is that you are looking for the region here to the right side, the right tail. Now let us first calculate the Z value. The mean we have is 105. You know the formula, I'm sure. 105 minus hypothetical mean 100 upon standard deviation of the mean, that is 20, divided by square root of the sample size, which is 50. Now if you simplify this, it gives you, and whatever the result comes, follows normal distribution with mean 0 and variance of 1. So the result would be 1.768. Now how do we solve this? Now this is the test statistic. Let's see. So it's approximately 1.77, 1.7, 1.7 gives you 0.9616. So since we are interested in this region, this one, so it's going to be 1 minus the value that we see here in the table, the Z table, that's 0.96. It means the result is 0.0384, which is less than 5%. It means it falls within this region. So the p-value, it is less than 5%, so we have sufficient evidence to reject the null hypothesis at 5% level of significance. This was the first approach using the p-value. We can alternatively solve it using the critical value. How does it work? We can use this way. We can calculate the 5% probability, that is 1 minus 5% gives you 0.95. So if you just look at the table in the reverse order, the 0.95 comes approximately at this point, which is 1.64. So our test statistics which we calculated previously, 1.77, it is greater than this critical value. So it means that we have sufficient evidence against H0. So whether you use p-value or critical value approach, in both cases we conclude that average IQ of CFA charter holders is greater than 100. Okay, now this is your next LOS. It says identify the appropriate test statistic and interpret the result for a hypothesis test concerning the population mean of both large and small samples. This is the LOS very much related to your previous reading regarding t statistics, t distribution and normal distribution. So when the population is normally or approximately normally distributed and the variance is known and unknown. In the first case, if the underlying variable is normally distributed, the ideal hypothesis test is z-test, whether the n is less than 30 or n is greater than 30. So in this case, our null hypothesis is mu is equal to hypothetical or assumed mean. When variance is known, we use t-statistic. This is how we calculate the z-score. This x bar represents the sample mean. H0 is the hypothesized mean of the population, the standard deviation of the population, and of course n is the square root of the sample size. We've already discussed this. So what we do, once we computed the z-statistic, we compare this with the critical value that corresponds to the level of significance, 5% or 1%, whatever it might be. For example, if the significance level is 5%, the z-statistic is screened against upper or lower 95% point of the normal distribution. We just done it. And the decision rule is reject the null hypothesis if z-statistics fall within the critical region. We just did it in the previous question. Now this is important. If the underlying variable is normally distributed and the population variance is known, then you use the z-statistics, we use the z-distribution. But if the population variance is not given, that is the topic for our next slide. When the variance is unknown and the distribution is normal or approximate normal and the sample size is less than 30. So when variance is unknown in this case, but the underlying distribution is either normal or approximate normal, we use what you call the t-test or t-distribution. We compute t-statistics with n-1 degree of freedom, this discussed in our previous reading. Here x bar is the sample mean, mu naught is the hypothesized mean of the population, s is the standard deviation of the sample. Since we do not have the standard deviation of the population, so we use standard deviation of the sample, and n is the square root of the sample size. So we'll do the same thing. Once the t-statistics computed with the same thing, it's compared to the critical value that corresponds to the level of significance, and finally the decision rule is reject null hypothesis if t-statistics fall within the critical region, something similar to what we've done in our previous example. Now let's say we have some questions to enhance our understanding. Using historical data, the hedge fund manager designs a test of whether abnormal returns are positive on average. The test results in a p-value of 3%. The manager can most appropriately reject the hypothesis. that abnormal returns are less than or equal to 0 using 1% significant level. Since we are talking about a p-value of 3%, so then it has to be a 5% level of significance. So 1% would be too narrow. So reject the hypothesis that the abnormal returns are less than or equal to 0 using 5% level of significance, because your p-value has to fall. If you remember on previous LOSs, your p-value has to be within the critical region in order to reject the null hypothesis. And since 5% level of significance means that either upper tail or lower tail or left or right tail, it will fall within the critical region. So B is the right answer. It's a straightforward question. An analyst wants to test a hypothesis concerning the population mean of monthly returns for a composite that has existed for 24 months. The analyst may appropriately use a t-statistic, t-test, but not a z-test if the returns for the composite are normally distributed. Yes, if the sample size is less than 30 and the population variance is not known, we can use t-statistics. With so small sample size, t-statistics may be used if the population is approximately normally distributed. Either t-test or a z-test if the returns for the composite are normally distributed. Now, this is not true. If the population variance is not known, we can't use z-test. So this is wrong. A t-test but not a z-test, regardless of distribution of wrong. This is again wrong if the distribution is normally distributed, and even if it is, if the n is greater than 30, we can use normal distribution. But if the population has a non-normal distribution, then no test statistics is possible, not t and not even z. So that makes A to be the correct option. Next, question number 3. Use the following segment of students' t distribution for question number 3. We have been given the level of significance for one tail and two tail, and we have been given the degree of freedom. From a sample size of 14 observations, an analyst calculates a t-statistics to test a hypothesis that the population mean is equal to 0 if the analyst chooses 5% significance level. 5% significance level in case of one tail test, so it's 0.25 is 2.5, 2.5, and in case of two tail test, it's 5%. So we have a total 14 observations. So I hope you remember the degrees of freedom is n minus 1, that is 14 minus 1, that is 13. So 13 at level of significance 5%, it's 2.16. So what is the answer? The question was, if the analyst chooses a 5% significance level, the appropriate critical value is greater than 2.15. That makes B to be the correct option. Next, LOS. Identify the appropriate test statistic and interpret the results for a hypothesis test concerning the equality of the population means of two at least approximately normally distributed populations based on an independent random samples with equal assumed variance or unequal assumed variance. Now let's say analyst may want to establish whether there exists a significant, let's say we have two different populations. So we want to establish whether there exists a significant difference between the means of these two populations. That's what we want to do. So let's say we are talking about a group of firms and there's a parent P incorporated, and these are the two subsidiaries, subsidiary 1, subsidiary 2. So we want to know whether the average returns for these two subsidiaries S1, S2, do they exhibit significant difference? Such analysis can be very helpful for us. Maybe we have limited resources, so the result from such test can help us decide on a resource allocation, that how many resources should we allocate to S1 and how much proportion should we allocate to S2. So in scenario 1, the difference between two population means small samples with a common pooled variance. Now let's say these are the two populations we are discussing. Let's say we select N1 samples from this population. That's a sample size for population 1, and N2 for the second population. And these are the sample means of population P1, P2, right? And let's say the population variance is sigma 1 square and sigma 2 square. We are assuming that these two variances are the same. There is a common variance. So our null hypothesis here is that the difference between the population mean is 0. Now in this case, we use the t statistic with n1 plus n2 minus 2 degree of freedom. Since there are two populations, remember from the previous learning outcome statements, n minus 1 is normally the degrees of freedom. Since there are two populations, so n1 minus 1 and this n2 minus 1, so when combined it gives you n1 plus n2 minus 2. So this is the t statistic with n1 plus n2 minus 2 degrees of freedom, and this is how we will calculate the t statistic. All the numbers we have, we will of course solve this or use this formula when we will do the actual questions from the end of chapters curriculum questions, and where n1, n2, x1 bar, x2 bar, they were already discussed in the previous slide. So we can then compare the test statistics with the relevant percentage point of the t distribution. So in this case, remember the decision rule is reject H0 if the test statistics fall within the critical region. So we will apply this idea as we go along, right? So remember here S1 square, S2 squares are the sample variances. Now scenario 2, the difference between two population means when the sample size is large. So basically again we have two populations, right? We draw sample size n1, n2 from these population with means x1, x2 and unknown variances respectively. Since we have large samples as agreed in the scenario 2, we can use sample variance as an estimate of population variance, and this is because of central limit theorem, because we know when the sample size is sufficiently large, then we can estimate this as distribution as a normal distribution. So again here the null hypothesis would be that mu1 mu2 is 0, and in this case, since the sample size is large, we will use z statistic, and in this case the decision rule would be reject the null hypothesis if z statistics fall within the critical region, right? Okay, and of course this is how we will use this formula to calculate the z-score. All these numbers I'm sure you have it, and just plug it in z and then use the table to find the values. Next, LOS, identify the appropriate test statistic and interpret the result for a hypothesis test concerning the mean difference of two normally distributed populations. Identify the appropriate test statistic and interpret the results for a hypothesis test concerning the mean difference of two normally distributed populations. Well, when testing for the difference between means of two different populations, the real difference can be masked by variability within each sample caused by factors other than they are of interest to the researcher or to the analyst. So a paired data test solves this kind of problem. For example, an analyst wishes to establish whether any difference exists between pre-dividend and post-dividend share price within an industry. That's what he wants to establish. So the analyst may collect stock price samples, say 7 days before dividend announcements, and repeat the process 7 days after the announcements. So as such, the analyst would end up with paired data from each sample company from which he can then perform the test. Then we come up with this basic situation. The null hypothesis is that your mu1 minus mu2 is equal to 0. Since the sample size is small, so you'll use t statistics where n minus 1 is the degree of freedom, and I'm sure you know the rest of it. This is all repetitive. Next LOS is identify the appropriate test statistic and interpret the results for a hypothesis test concerning the variance of a normally distributed population and the equality of the variances of two normally distributed populations based on two independent random samples. So what we're talking about here, a chi-square test now is an alternative, is used to establish whether a hypothesized value of variance is equal to or less than or greater than the true population variance. Now why chi-squared test? What is it? Why not z-test or the t-test? First of all, unlike most distributions, the chi-square distribution is asymmetrical. It has no negative values. The basic situation in chi-square distribution is that your null hypothesis is that hypothesized value of variance is equal to the true population variance. So the chi-square statistics is given by this formula. We will learn, we'll do the questions, then you'll know how do we apply this formula. Here n is the sample size, this is the sample variance, and this is the hypothesized population variance. In chi-square test, we will use chi-square distribution. How we will do, you'll learn just a little while later. We'll just do some questions and some examples, and of course many questions in your end of chapter questions extracted from your CFA curriculum. So we will compare the chi-square with the appropriate percentage point of the chi-square distribution to determine that whether should we reject or not reject the null hypothesis. So this will be discussed as we go along. Alright, next, testing the value of the ratio of two population variances. Testing the value of the ratio of the two population variances. Alright, compare two independent random samples of sizes n1 and n2, and they have been extracted from distribution with mu and this variance, and the second one mu2. Right. Let us say that we have the sample variances of s1 square and s2 square. The basic situation involves this hypothesis, null hypothesis, that variance 1 is equal to variance 2, or the alternative hypothesis that variance 1 is not equal to variance 2. So since we are now talking about two population variances, the ratio of two population variance, so for this we have a new distribution called the F distribution. So this is basically what you see here. S1 squared, S2 squared is basically the F distribution. The decision rule in this case is reject the null hypothesis if the test statistics fall within the critical region of F distribution. What it is all about, we will do all the questions related to this LOS, and that will further clarify the concept. Now here's an example for you. For the 15-year period between 2000 and 2015, HKK's monthly return had a standard deviation of 5%. Matthew Brown, a financial analyst, wishes to establish whether the standard deviation witnessed during that period still adequately describes the long-term standard deviation of the company's return. He collects data on the monthly returns recorded between 1st of Jan 2016 to 31st of December 2017. Basically 24 months are involved, and computes a monthly standard deviation of 4%. Now what we have to do, carry out a 5% test to determine if the standard deviation computed in the latter period is different from the 15 years value. Now this is basically a chi-square test on variance. Let us set up the hypothesis. Our null hypothesis is that variance is equal to 5% squared, which basically means 0.05 squared, and that will give you 0.0025. The alternative hypothesis is that variance is not equal to 0.0025. Now the period n is 24. We can now calculate the chi-square test. We know the formula. This is the formula we just discussed a little while ago. Degrees of freedom. Just plug in the numbers. Alright, so n here is 24. 24 minus 1. Standard deviation, the sample standard deviation is 4. 4% squared, it will be 0.04 squared, and that will give you 0.0016. And divided by the variance of the population hypothesized, that's 0.0025. And if you simplify all this, you get 14.72. Now this is a two-tailed test. As such, we have to divide the significance level by 2 and screen out test statistics against the lower and upper 2.5 points of x squared to 23. That's the degree of freedom, 24 minus 123. So let's consult the table. Now consulting the chi-square table, the test statistic that we calculated previously, 14.72, it lies between the lower, this is the degree of freedom, 97.5 and 2.5%. So it lies between the lower value 11.689 and the upper value of 38.076. So now, since our test statistic here lies between the lower and the upper points of the chi-square distribution, basically which is your non-rejection region, thus we have insufficient evidence to reject the null hypothesis. So the conclusion is that the standard deviation value is close enough to the 15 years value that we discussed. This is your last slide. Then we have to distinguish between parametric tests and non-parametric tests. So parametric tests are statistical tests in which we make assumptions regarding the distribution of the population. For instance, we might assume that the underlying variables follow a normal distribution. In that case, we use Z statistics or then T or and so on. Non-parametric tests, also called the distribution-free tests, are tests that do not make any assumptions regarding the distribution of the parameter under study. So analysts use non-parametric testing when the median is more desirable than the mean, or when the sample size is extremely small, maybe say less than 10 observations, or the data under analysis is ordinal, ordered where the variables have natural ordered categories and the distances between the categories is not known. So that ends your overview of hypothesis testing. This, I believe, is hardly 10 to 15% of what should be learned. The remaining 85 or 90% would come from doing lots of questions. Your curriculum questions, all questions will be done in detail. So if anything is left out in the overview, it will be covered in the questions.